Welcome you all to this lecture 9.4 on short circuit test of transformers. Earlier in lecture 9.3 we have discussed about the open circuit test or no load test. Now no load test is done on low voltage side and high voltage side is kept open. Now we will talk about the short circuit test. Before that, why this test is performed, basically in the last lecture 9.3 we have discussed that open circuit test or no load test is done basically to find the coal loss or we say iron loss and no load power factor. No load power factor. Also the magnetizing current and IMIW, this no load primary current, magnetizing working current or active current, magnetizing current, all this could be found out from no load test. Now let's see what other parameters remains can we find out from this short circuit test. So short circuit test, basically the main what we can find out is that full load copper loss, full load copper loss, and other transformer parameters like referred to the high voltage side, or we can say in which side we are performing the experiment, that side we can find the equivalent. Already we have discussed in the lecture equivalent circuit. So equivalent circuit parameters like R and X, and Z impedance. So resistance, reactance and impedance referred to the side on which instruments are connected or measurement is done. Measurement is done or experiment is performed. Experiment is performed. So once we have this all these parameters, then we can find basically what we can find the efficiency of a transformer, efficiency and voltage regulation. And both without actually loading the transformer. Without actually loading the transformer. Why this is important? This is important because in case of a very high rated large transformer, if we have to actually load it, then that will take a huge amount of power, and that power will cost huge money, and at the same time that amount of load is not easily available. You cannot manage that amount of load for a like a MVA megavolt ampere capacity of transformer. So that much amount of load, that is not possible to create in a laboratory or experimental purpose. And similarly that amount of energy will be wasted. That is also a huge cost. So this test has the advantage of doing performing the test and getting the parameter values without actually loading. So the energy cost or the supply power we have to provide to conduct these two experiments is very less in compared to actually loading the transformer. So it is cost effective also and can be done in a smaller test environment. So let's see now what happened in short circuit test. Very first important point in this case is that this short circuit test is done on, let's say we say SC, we will say short circuit test, SC test. It is done on the high voltage side, and low voltage side is short circuited. is short circuited. Short circuited using thick wire, thick conducting wire, because a high amount of current will flow, so we need thick wire. Here we have shown that the low voltage side is short circuited using very thick copper wire. So high current will flow, a thick copper wire will allow it to flow high amount of current. Fine. And in the high voltage side we will be performing the test. So for that we need this. For the high voltage side we need to measure the current, rated current, that is I1, actually primary rated current. Here we will call it ISC. Let me write this. ISC will be, ISC is basically nothing but the rated primary current, that is rated primary current, rated primary current that actually that should flow when the full load is, rated load is applied in the secondary. But we will do some other way, but we will make sure that rated primary current is flowing through I1. How we will arrive this rated, I will tell. Next we have connected a voltmeter to measure the input voltage. We will call this voltage as VSC, that is the VSC will be a voltage on primary that produces this rated primary current, in the through the primary winding, through the primary winding. And we need to measure the here we see that we have also connected one wattmeter that will estimate, that will measure the input power. So WSC measures the input power to the primary. Now let's say actually what happens, and also this is an auto transformer. So what we can do, we have applied the supply voltage here, and using this auto transformer we can provide reduced voltage to the high voltage side. And what we do, we actually start with very small amount of voltage and we keep on checking this current ISC. Then we increase this voltage a little at a time and we check the increase in current. When the current reaches the actual rated primary current, now how we get the rated primary current? Rated primary current we can get from the transformer rating. Like suppose the transformer rating is it is said 250 volt by 1000 volt and 250 kVA. This is the transformer rating. Then what will be the rated primary current? Then the rated primary current, let's say I1, that is primary current, will be 25 into 1000 divided by 250, that is 100 ampere. So what we will do here, we keep on increasing this voltage, short circuit voltage, and as we keep on we start from very low voltage and then keep on increasing this voltage, and this current will increase at some voltage we will get at, that is VSC, on which the current in the primary side will be ISC, that is the rated current, that is in this case for our example suppose 100 ampere. So we stop there. So for that voltage will become VSC. This voltage, it is seen that this voltage will be actually very less than the rated voltage. For our example, rated voltage we have seen that is 250 volt. But in this case, VSC may be maximum up to 5 to 10% of that. But maybe with 20 volt, we may reach the current of 100 ampere. Because secondary side, there is no load, that is short circuited. That is why with very less voltage we will get the required rated primary current. Then the current in the secondary will also be the rated current. Why? Because this turn ratio, we already know that the ratio is I1 I2 by I1 is basically N1 by N2. This is opposite. So in this case I2 will be N1 by N2 into sorry I1. So if this is 100 ampere and then this side rated current, if turn ratio multiplied by turn ratio, that is the current we will get here will be the actually rated current. So if we go to our example, the rated secondary current will be what? Rated secondary current will be 25 into 1000 divided by 1000, that is for 25 ampere. So here turn ratio is actually 1 by 4, 1 is to 4. So in that case I2 will be 25 ampere. When this is 100 ampere, then this I2 will be 25 ampere. So this is also rated current. So now what we see that the in this setup VSC may be 20 volt. Due to 20 volt of current, the primary is flowing, in the primary circuit the current is rated current 100 ampere. Also in the secondary circuit rated current is flowing. So if we say the copper losses, now let's say copper, what will be the copper losses? So this input power, so let's say copper losses or winding losses, copper losses or I square R losses in the winding. What will be the total value? Total value will be, suppose this is PCU, copper loss. So total value will be primary side rated current I1 square into R1 plus I2 square into R2 secondary rated current into this. So this will be the total copper loss. Now actually the whole supply, the power we are supplying, that supply is going for two purposes: to supply these two copper losses, and at the same time it is supplying the copper losses in primary and secondary, and also very small amount of core loss, that is the hysteresis and eddy current loss. Now hysteresis and eddy current loss depends on the voltage. In this case this voltage is very small, so this hysteresis and eddy current loss will be very small compared to the rated copper loss, because rated current is flowing, so copper loss will be much more greater than the iron loss. So for the purpose we ignore the coal loss or this iron loss, eddy current and hysteresis loss, as that will be very small. So effectively what we get here, the wattmeter reading we call it as WSC. This wattmeter reading is nothing but the total copper loss, that is this copper loss in the primary circuit and secondary circuit. So we get the total copper loss in the wattmeter reading that is connected in the primary. Now let's say the how we will calculate other things. So calculations are very easy. Now we got this one copper loss, and now if we say that as we have done all the testing in the primary side, so we can also write this as I1 square into R01, where R01 is the equivalent resistance. R01 is the equivalent total resistance, referred to primary. So if you are not understanding this, you should check out the lecture on transformer equivalent circuit. So all this secondary circuit resistance could be referred to the primary, brought to the primary, and then we get R01, that is actually the equivalent resistance. If we put R1 and referred R2 to the primary side, then the total resistance we get is known as R01, that is the equivalent resistance. So that is into I1 square. So in this way we can get the primary side equivalent resistance as WSC by I1 square. So that is one of our goal, that is we got the full load copper loss and R. Next, we want to find the reactance. So primary side reactance, what will be the primary side reactance? Before that, we will calculate the primary side in impedance referred to the primary side. So that will be basically VSC divided by I1. So that is I into impedance, current into impedance is the voltage. So the impedance will be referred to the primary side, total impedance referred to the primary side, Z01 will be equal to the short circuit voltage divided by the ISC, or we can say I1, the rated primary current. So we get Z01. Again, we know another relationship between the impedance, that Z is equal to basically Z square is equal to R square plus X square. So from this formula, we can also find out what will be the X01, that is the leakage reactance referred to the primary. So let me write it here. X01 will be square root of Z01 square minus R01 square. So this is nothing but the leakage, total leakage reactance referred to the primary. So we see that it is possible from this test, short circuit test, to compute the full load copper loss, that is the wattmeter reading, WSC reading, the equivalent circuit parameter R. In the primary side, there is R01, X01 and Z01, and from no load test all this. So in a next video, another video, we'll see how all these values could be used to calculate the voltage regulation. Efficiency, we have already talked about efficiency in a video lecture 6.2, and in another video we'll talk about voltage regulation, how from all these parameters we can find out the voltage regulation of a transformer. So thank you.